Hello everyone, I'm Jiazhou Liu from Monash University. Today, I'll be presenting our DataDancing project in collaboration with Barrett Ans, Arno Purzu, James Smiley, Isabel Nixon, Sarah Goodwin, and Tim Dwyer. In this project, we explore the design space for whole-body interactions and propose hybrid prototypes for designing visualization view management for 3D surfaces and spaces. Recent studies have explored how users of immersive visualization systems arrange visualization views in the space around them. Generally, these systems focused on visualization views centered at eye level in absolute room coordinates and interactions via handheld controllers. However, immersive technologies offer the opportunity to work with visualization views with natural embodied interactions using different body parts. For example, foot interaction in general HCI has been explored as an additional input channel for complex tasks or when both hands are occupied. The whole body can also be used as additional modality to support implicit tasks using proxemic interaction. These novel interaction design possibilities represent a significant shift from everything we have learned about interaction with flat screens. In this paper, we first introduced a design space for visualization view management, presenting a framework that identifies important aspects in whole-body interactions for designing view management systems. During this process, we investigate existing designs from an extensive review of literature. We distilled a set of design dimensions using a bottom-up open coding approach by categorizing existing designs among these dimensions to identify gaps and common usages. This process results in 11 design dimensions in two categories: visualization view presentation and user interactions. In the visualization view presentation, the perspective refers to the cognitive judgment of view locations from either an egocentric perspective or an exocentric perspective. Proximity refers to the distance relationship between the user and the visualization views. The view movability refers to whether each visualization view has both position and orientation fixed, free orientation pivoting, or free movable. These three dimensions are grouped as space perception. The second group is the frame of reference, including the dimension of the coordinate system, the curvature, orientation, and the movability of the reference frame. For user interaction, there are two groups as well. In the interaction style group, the degree of intent refers to the intent of the interaction, either explicitly initiated by the user or implicitly mediated by the system. Proxemics refers to the study of space and how we use it. In the action group, the input modality covers a wide range of interaction modalities, and the target design dimension describes the target of the action. This table illustrates how the existing view management systems align with our design space. For example, in MX's and Fiesta systems, visualization views are exocentric to the virtual world or objects in the world, such as walls. The views are near the users, allowing direct interaction with them. All the views can be freely moved and oriented. The main reference frame of the views is the fixed 3D virtual space, normally flat and vertical. All interactions are explicit and no proxemics are applied. Users perform the action by hand and target the views directly. Another example is the variable conferencing space. The views are displayed egocentrically and fixed to the user. Users can only change the orientation of the views which are close to them at eye level. The reference frame is a one-dimensional curved and vertical line. The reference frame can be moved with the users. Users can perform explicit interactions on the reference frame by changing the orientation of their whole body. We then extrapolate several view management prototype surfaces from these existing designs, each demonstrating a different combination of interaction techniques and space use. These surfaces include wall displays, floor displays, tabletop displays, body-fixed large displays, and body-fixed cockpit displays. We then conduct a user study that explores and evaluates the usability of 4 combinations of these surfaces. In order to simulate a real working environment for visualization view management tasks and to follow the design guidelines for multiple views, we consider two fixed semantic levels for the information contained within the views. For example, in the top left figure, a tabletop display is used as a landmark for users to interact with directly, while a wall display is used as a coordinated, detailed view, which contains more information for analysis and sense-making. We designed 4 such combinations and conducted a within-subject study to evaluate the presentation and interaction with each display surface. We recruited 12 participants and collected quantitative data, qualitative feedback, and rankings for the 4 prototypes after completing a series of designed view management tasks, such as finding the extreme values or trends over time from multiple views by navigating, rearranging, highlighting, or sorting them. The study uses a novel body tracking system and foot pressure sensors to track participants' torso and feet positions. From our study, we observed novel behaviors and collected feedback from participants with a set of interface design implications unique to visualization view management. Firstly, participants suggested having world-fixed exocentric display surfaces, such as a wall display, for collaboration use, while body-fixed egocentric display surfaces, such as a cockpit display, for private use. Secondly, most participants preferred the curved surfaces, reporting that views on the curved surfaces are close to them, which offers easy and quick selection. This finding aligns with our previous research that semicircle layouts perform better on visual analytic tasks than other layouts and are more preferred by participants. Lastly, participants have mixed feedback on the evaluated novel interactions, such as the foot interactions. On the one hand, participants were not familiar with and unconfident with the foot interactions and reported neck strain while looking down at the ground. On the other hand, most participants felt the foot interactions were intuitive and easier than expected. Our qualitative results align with the related work that users can perform high-precision interaction tasks using their hands. In contrast, foot interactions can support secondary navigation tasks such as panning and zooming. Learning from the user study, we improved the interaction techniques and proposed 2 hybrid prototype interfaces that demonstrate the interaction possibilities of our design space. In the first prototype, Joe wants to find the day in December when his favorite street has the most pedestrian volume. Joe is standing in front of visualizations showing the pedestrian volume in December. The visualizations are in a small multiples layout on a wall display. This wall display can also be used in a collaborative environment. He uses bi-manual hand interaction to change the aspect ratio or pan the whole wall display, so that he can see everything at eye level. After scanning through the visualizations, he clicks on the bar which represents the data for his favorite street on the chart. Then, he drags visualizations from the world-fixed wall display to a body-fixed cockpit display. The cockpit display is a personal workspace that others cannot see. Then, he uses the foot interaction to pan the cockpit display and to change the geometry, especially when his hands are occupied with other charts. After comparing all selected charts in his private workspace, Joe finds the answer. The second prototype uses proxemic interaction to interact with views and switch between different surfaces. Here, we have Patrick, who would like to walk close to a wall display and see the visualization clearly. When Patrick moves closer to the wall display transforms into a curved tabletop display, which allows him to have the same distance to all visualization views. Patrick keeps moving, and the geometry transforms from a semicircle to a full circle. Then, the tabletop display becomes a body-fixed cockpit display, which follows Patrick. All the interaction in this prototype is implicit using proxemics. In summary, our DataDancing is the first to explore the effects of foot interactions on floor displays for visualization view management in 3D space. Future work involving the full 3D space may consider designing effective foot gestures and using them as an additional input channel for assisting other modalities.